This is basically the same problem we solved in the last video. In the last video, they were asking for speed and we used energy. I've changed it slightly. In this case, we're not interested in the time when M2 gets back to its equilibrium position. It starts up here, a distance d from its equilibrium position. We release the boxes. M2 starts to go down. And what we care about now is the point when it's halfway back to its equilibrium position, d over 2. So it's going to be moving down, and M1 is going to be moving up the incline, and the spring will be stretched by a distance d over 2. And this time we want to know the acceleration of the boxes at that instant and the tensions in the string at that instant. Now, an instant before, they're going to be different. An instant later, they're going to be different because we have a spring in our system, and a spring does not exert a constant force. But we can solve for them at this instant. We're going to use our dynamics lens because we're looking for acceleration and forces, and we know F equals ma is an equation that incorporates both of them. So for every mass in our system, we'll start out by drawing a free body diagram. And for every mass in our system, we're going to get an equation. So we have 2 boxes and a pulley. We have 3 masses in our system. We'll have 3 equations. We can solve for 3 unknowns. And that's how many we have. The acceleration is 1 unknown, and the tension in that rope is going to be different on each side of the pulley. I'll call this T1, the rope that's attached to mass 1, and I'll call this T2, the rope that's attached to mass 2. So we can solve for T1, T2, and the acceleration. Those are our 3 unknowns using our 3 equations from the masses. We'll start with our free body diagrams. Let's start with box 2. I always ask, what's touching box 2? Well, we have a string touching it right here. So we're going to have tension, and we're calling that T2. The rope attached to box 2, T2, and the rope attached to box 1, we're calling that T1. So we've got T2 pulling up. What else is touching it? The spring is touching it. And in this case, M2 is above the equilibrium position of the spring. So the spring is stretched, which means it's pulling down on M2. That's everything that's touching M2. What can reach in from a distance? Gravity. So I have 2 different tensions in my system. I know that. So I'm using different subscripts. I'll have T1 and T2. I have different masses in my system, so I have to have different subscripts so I know which one I'm talking about. But I only have 1 spring force in my system, so I'm going to leave the subscripts off there. It's clear that that's my spring force. What's touching the pulley? T1 and T2, and the pulley's being held up at its axle with some kind of a support force, probably something like this. That's everything that's touching the pulley. What can reach in from a distance? Gravity, and that acts at the center of mass of the pulley. Now let's take a look at M1. M1 is on an incline. Let's take a look at what's touching M1. We have the hand exerting a force on M1 in this direction. We have the rope T1 exerting a force on M1 up the incline. We have the surface touching it. That can interact 2 ways, through a normal force and through a friction force. And M1 is sliding up the incline, so our friction force is going to be down the incline. There's only 1 normal force in my system. There's only one friction force. I don't need subscripts there. What can reach in from a distance? Gravity. What directions do I want for my coordinate system? Well, I always pick the direction of the acceleration if I know what it is. I know this has to be accelerating in this direction along the incline. So I'm going to pick this as one of my directions and perpendicular to that as the other direction. I like to call this the parallel direction, parallel to my acceleration, parallel to my direction of motion, and perpendicular to that. So I can redraw this diagram. The normal force is already in this coordinate system. I don't need to use components, as are these other forces. The only one I need to split up is my force of gravity, cosine theta, and an FG1 sine theta. Now that I have my free body diagrams drawn, I say sum of the forces is equal to ma. And I'm going to start with mass number 1. This is a vector equation. So I break it up into my components. Sum of the forces parallel to the acceleration is equal to m1 times a. It's accelerating in that direction. And sum of the forces perpendicular to that direction has to be 0. That's why I pick parallel and perpendicular, because I know all of my acceleration is in one direction and the other direction has 0 acceleration. Why do I do this? To find the normal force. Why do I need the normal force? Because there's friction in my system. So I'm going to say that's my positive direction. And I've got a normal force pointing in the positive direction. And in the negative direction, I've got an m1g cosine theta. Those have to add up to be 0. So I've got a normal force is m1g cosine theta. Now I look at my parallel direction. I'm going to say up the incline is my positive direction. So that's this direction. And I've got a T1 in the positive direction. And in the negative direction, I have 3 forces: F hand, kinetic friction, and the weight that's going down the incline, m1g sine theta. And I add those all up, and I have to get m1 times the acceleration, m1a. So this is one equation. Let me continue. I have a friction force here I can substitute in for. So I've got my tension, my F hand. Friction force is going to be mu times my normal force. And then I've got the weight in that direction, m1 times its acceleration. So that's one equation, but I've got 2 unknowns. I've got acceleration and T1. I need another equation. So I go to m2, and I say for m2, sum of the forces has to be its mass times its acceleration. And m2 is only moving in one direction. I don't need to split this up. This is all the parallel direction. There is no perpendicular direction. m2 is only moving in this direction. And I am going to pick, you could pick any direction you want to be positive for this, but it's very beneficial to get all your accelerations to be the same. And in order for your accelerations to be the same, you have to be careful the way you pick your positive directions. So for m1, we said up was our positive direction, up the incline. That's fine. We could have said anything we want. I picked up the incline as my positive direction. that fixes the positive direction for everything else. When M1 goes up the incline, what happens to my pulley? It rotates counterclockwise, or it has an omega out of the page using our right hand rule, and M2 goes down. So if I pick counterclockwise or out of the page as my positive direction for rotation for the pulley, and if I pick down as my positive direction for M2, then they match the positive direction for M1. When M1 goes in the positive direction, everything else has to go in the positive direction for the accelerations to be the same. And I want the accelerations to be the same because I'll forget that one is positive and one is negative, and I'll forget that later. I want the accelerations to be the same. So therefore, once you pick the first one, that fixes the positive direction for everything else in your system. So that means that down has to be my positive direction if I want my accelerations to be the same. So I look at my free body diagram. I see I have two forces in the positive direction, the spring force and the weight of mass 2, and one force in the negative direction, T2, and those have to add up to be M2 times the acceleration. So I have one equation here with two unknowns, A and T2, and I have one equation over here with two unknowns, A and T1. I need one more equation that links T1 and T2. So let me go to my third mass, the mass of the pulley, look at the free body diagram, and I'm going to write an equation for that. Now I'm not going to use sum of the forces equals MA because I know my pulley is not moving anywhere. What I'm going to use is sum of the torque equals I alpha. And what direction is positive? I'm going to pick counterclockwise or out of the page as my positive direction because that's fixed by the other masses moving in their positive directions. So sum of the torque. What do I have? I've got torque caused by T2 is going to be the force, T2, times its lever arm. And its lever arm is just the radius of the pulley. That's in the positive direction. It's causing this to rotate counterclockwise, or it's causing it to turn with an omega out of the page. Then I've got T1 causing it to turn in the negative direction. So minus T1 is the force times its lever arm, R, gives me the torque produced by that string on that pulley. Now I could also write F support times its lever arm. But what is the lever arm for that? That force passes right through the axis of rotation of the pulley. Its lever arm is 0. And I could also put the weight times its lever arm, but the weight also passes right through the axis of rotation of the pulley. So they don't produce any torque. I'm just going to leave them out of my equation. And this has to equal I times alpha. So I've got T2 minus T1 times R is I for the pulley. The pulley is a solid disk, so that's 1/2 M pulley R squared is I times alpha. And we know that alpha and A are related. What's the acceleration of the masses? It's the same as the acceleration of the string. And the string goes over the rim of the pulley. So what's the tangential acceleration at the rim of the pulley? It's R alpha. So I can substitute in here A over R for alpha. When I do that, the R's all cancel out, and I get T2 minus T1 is M pulley over 2 times A, and that's my third equation. and I'm finished with this problem. So you want to take a look at the problem. What is it asking for? Figure out what lens you're going to use. If you're using an energy lens, I highly recommend making that bar chart at least the first 5 or 6 times you solve complicated energy problems. After that, maybe you can go without it. I kind of view that energy bar chart as training wheels. When you first start riding a bicycle, those training wheels are really helpful. After a while, you don't need them anymore. That energy bar chart is the same. When you first start doing energy conservation problems, it really helps fix your mind to think about the problem the right way. After you do half a dozen problems or so, maybe you don't need that bar chart anymore. You can go right to the equation. And when you're doing a dynamics problem, every mass in your system is going to give you an equation. You can solve for the same number of unknowns as you have masses in your system, and that includes the pulley. So in this case, I had 2 boxes and a pulley, 3 masses. I could solve for 3 unknowns. I start by drawing free body diagrams, and then I say sum of the forces equals ma for things that are moving, and sum of the torque equals I alpha for things that are rotating. And I know there's a link between the two where the rope goes over the pulley.